let's continue here with section 3.3 and do a bit more optimization problems here, specifically for business applications. But before we do so, let's look at another concept, the second derivative test. Now we have looked at the first derivative test where we draw a number line to help us determine whether at a certain critical number we have a maximum, a relative maximum, or a relative minimum point. The second derivative test is also a test for relative extrema. Be careful, the second derivative test is not for concavity. It is still for relative extrema to determine where we have a relative max or a relative min. And how we go about this is by doing the following. If x equals c, where c is a critical number, if x equals c is a critical number of a function of x, and the second derivative of that function is defined, then the following can be tested. If we plug in this critical number and evaluate it using our second derivative, make a different color for this one. If our critical number evaluated using our second derivative is greater than 0, then this means that our function of x, our original function of x, has a relative minimum at that critical value at x equals c. Okay? If our critical value gives us a positive number in our second derivative, then that means that critical value is a relative minimum. Recall what it means for our second derivative to be positive from section 3.2. Recall what it means for the second derivative to be positive. If the second derivative is positive, that means our function is concave up. That we have an upwards parabolic type of shape. And if it's concave up, if our concavity is upwards and c is a critical number, then that means that c here has to be the minimum point of that concave up shape, of the concave upward shape. So here we have c. So c is the minimum point of our upwards concavity. Okay, so if we plug in our critical number into the second derivative, and that gives us a positive value, that is implying that our function is not only concave up, but that the critical number is the minimum point of that upwards curve. Okay, now, if it's negative, then that means we're gonna have a relative minimum. Right, if our second derivative evaluated at a critical point represented by c is less than 0, then it means our function has a relative maximum at x equals c. Again, we call it from section 3.2. When our second derivative is negative, that means our function is concave down, meaning we have a downwards curve. And if we have a downwards curve then, and this critical number gives us a negative value, that means that critical number has to be the high point, the maximum point of that downwards curvature. So C will be the relative maximum of this concave down shape. Okay, so this is another way we can determine whether the critical number will be a max, or be a minimum or a maximum, by plugging into the second derivative and see if it gives us a positive or negative value. If it's positive, that means the critical number is a relative minimum. If it's negative, that means that critical value is a relative maximum. Now the problem with this method, the second derivative test, is that we recall from section 3.1, a critical number does not always guarantee that we'll have a min or max. Sometimes we might have a saddle point, meaning it's neither max nor min. Okay, so this method is more applicable to more real world type of problems where we're trying to optimize a function and know that it has to be an optimal point. And if we wanted to quickly test to see if it's a max or min, we can use the second derivative test. All right, so speaking applications of optimization, let's talk about maximizing profit here. Let's see if we can fit it. I can probably fit on this page. All right, so let's talk about maximizing profit. Oops. Okay, maximizing profit. All right, and this can also be applied to maximizing revenue and minimizing costs, right? If you're a business, you want to maximize your revenue, you want to maximize your profit, and you want to minimize your costs. Now I'll focus on profit, but the methods I'm going to be using here can apply similarly to revenue and cost, which we'll do a few examples in the next section. Okay, now recall from chapter 2, profit. The profit of a business company is defined as your revenue minus your cost function. Okay, we call revenue represents how much money we get from selling X amount of units at a certain price. And the cost function represents how much money we're going to spend making these X amount of units. Okay, let's focus here on the revenue real quick. So again, what the revenue represents is how much money we make from selling X amount of units at a certain price. In other words, revenue can be defined as the unit price, the price per unit, also known as the selling price, multiply by the quantity of items, by the amount of items that we're selling. Okay, so let me make this selling price here. So again, the unit price is the same thing as the selling price. It's like, say for example, suppose we're selling like, say, t-shirts at $5 a piece, and suppose we're gonna sell 20 t-shirts. So 20 t-shirts at $5 a piece, that means our revenue will be $5 times 20. The price per shirt times the amount of shirts that we're selling. And that gives us the revenue that we make from selling those 20 t-shirts. All right, so again, the revenue is the amount of money that we make from selling X amount of units at a certain price per each. Okay. Now, what we're going to do here is we're going to define and introduce another function that's going to help us determine the amount of revenue that we make. And that function is going to be known as the price function. The price function, which is denoted as lowercase p. All right, not big P, but little p of x. All right, so little p of x, the price function, gives us the price represented by p at which consumers will buy exactly X amount of units. Just check if everything's working. All right, so the price function gives us the price at which consumers will buy X amount of units. Okay. And what we notice from businesses is that the price and quantity, the amount of units that consumers will buy, and the amount of price that we're going to be selling each per of the amount of price we're going to be setting for each unit, these have an inverse relationship. Price and quantity are inversely related. In other words, again, applying some logic here, the lower the price, the more we can sell. The higher the price, the less we will sell. All right, if we can, let me illustrate this relationship. All right, so here we have a y-axis and x-axis. For graphs, come on. All right, and suppose the y-axis representing the price per unit, and the x-axis is our quantity, the amount of units that consumers will buy, represented usually by x. So usually for this relationship, the lower the price, the more we sell. The greater the price, the less units that we sell. Okay, so these two items have an inverse relationship. So what we want to figure out is we want to find the optimal point for price and quantity that will help us maximize our revenue to help us maximize our profit. All right, so let me set up a little example here on how to find that price and quantity to help us maximize the profit. Okay, let's see. Suppose that, say, a certain company finds that it costs $200 to produce each bike that they want to sell. And suppose the fixed costs for making these bikes are $1,500 per day. All right. And suppose the price function for this company, the price that they're willing to sell these bikes at, is defined as P of X, where P of X equals 600 minus 5 times X, where X equals the number of bikes they want to sell. Okay, so our price function is given to us directly as 600 minus 5 times X. Okay, now, suppose for part A, we'll do several parts for this problem. Suppose for part A, let us define our cost function. Again, what the cost function represents is it represents the amount of money that we're going to spend to make X amount of units. So the cost function will be how much we're going to spend to make X amount of bikes here. Well, let's see what they tell us. First thing they tell us here is that it costs $200 to make each bike. So it costs the company $200 per bike. So let's start setting up our cost function here, which I'll denote as C of X. Okay, so we know from the information that's given to us, if we want to make X amount of units, it's going to cost $200 per unit. So 200 times X. But what else does it tell us? That we have some fixed costs that we also have to spend. And that fixed cost is $1,500 per day. Okay, meaning on a certain day, if we want to make X amount of units, no matter how many bikes we make, we have to pay a fixed cost, a single cost here of $1,500. So it's going to be 200x per 1 plus 1,500. So this is the cost per day for making X amount of units on that single day. All right, we're going to focus on just one single day here. So for one single day, we want to make X amount of bikes. It's going to cost us $200 per bike plus our $1,500 of fixed costs. All right, this could be like, say, the warehouse, the machines that we have to use, and so on. Now, for part B, let's define our revenue function. All right, we have our cost function, and now let's define our revenue function. And again, the revenue function represents how much we're going to make from selling X amount of units at a certain price, at a price point. In other words, our revenue function can be defined as our price function multiplied by our quantity. Okay, where usually quantity is represented by X. So price times quantity. All right, so look at our example here. If we want to define our revenue function, big R of X, we have to take our price function and multiply by the quantity of bikes that we're going to sell, which is being represented here by X. So price times X. So in this case, our price function, actually, let me rewrite this part, or I can't. Let me write it instead of, because it's going to be squaring stuff. So again, our revenue function R of X is going to equal our price function times our quantity, which this could be represented by X, the amount of bikes that we want to sell. So we're going to take our price function, which is given to us directly as 600 minus 5 times X, multiplied by X to give us our revenue here of 600X minus 5X squared. So that's our revenue function. All right, so here we have our revenue function, and here we have our cost function. Okay, and now for part C, now that we have the cost and the revenue function, we need one more function here to define, and that's the profit function. All right, and how do we define the profit function again? Revenue minus cost. All right, so don't forget that your profit function, P of X, can be defined as your revenue minus your cost. All right, so our revenue function, which we just found to be 600X minus 5X squared, minus our cost function, which we define in part A as 200X plus 1,500. Okay, and again, these functions are based per day. So this is the cost per day. This will be the revenue per day. And this will be our profit per day. All right, so be careful with the second part of this function. Don't forget, we have a negative in front of our cost function here. When that negative has to be applied to the first and our second term here. Okay, so that's going to give us 600X minus 5X squared minus 200X minus 1,500. Do not drop that negative sign. All right, so now combining like terms, we get our profit function here of, let's see, I'll put in descending order of power. So let's see, negative 5X squared plus 400X minus 1,500. So that's our profit function. Okay. Oops. All right. So here we introduce this price function that helps us define our revenue function. And then later on, probably in the next section, we'll talk about the quantity function. For now, our quantity is just X. Do you have enough room? Possibly. All right, so now for part D, let's figure out here for part D. Let us find the quantity of bikes to be sold and the price per bike that will maximize our profit. Okay. So we want to find the quantity of bikes and the price per bike that will maximize our profit function. Okay. So again, our profit function here, we define above as negative 5X squared plus 400X minus 1,500. And look at what we're trying to find here. we want to find first the quantity of bikes. And we want to figure out what X has to be in order to maximize this profit function. And then we find the price afterwards. Okay, so the first one to figure out is what does X have to be for this function in order to get the maximum value of our profit. So how are we going to do that? How can we figure out what X has to be to optimize this problem, to optimize this function? Again, what we've been dealing with throughout the whole chapter, optimization. What does optimization mean? What does it mean to optimize a function? To find its critical values. So what we have to do is find the critical value or values of our profit function. And how do we find the critical values of the function? By finding its derivative and solving for the zeros of the first derivative. So let's find the first derivative of this function. So P prime, capital P prime. All right, so the derivative of this function is going to be, let's see, negative 10x plus 400. Okay, just a straightforward derivative here. And now just set this equal to 0. So you can solve for critical numbers. And then solving for x gives us x equals 40. Okay. So here we have found our critical number. And what is that critical number telling me? This is telling me, based on what we have here, we're going to have to sell 40 bikes if we want to maximize our profit. But let's check to see if this is truly the maximum point here. And to do a quick check to see if this is going to give us our maximum value, our maximum point, we can use the second derivative test by taking that critical number, plug into our second derivative, and see if it will be a positive or negative. If the second derivative comes out positive, then that's a minimum value. If the second derivative comes back negative, then that critical number is going to give us a maximum value. All right, so let's do the second derivative test check real quick here. All right, so let's do a second derivative test. All right, so first we got to find the second derivative. So P double prime of x. The second derivative of negative 10x plus 400 is just negative 10. Which means then our second derivative evaluated at this critical value of 40. Well, since second derivative is just a constant, then at 40, our second derivative will still be negative 10, which means that it's going to be less than 0, which means that 40 will give us a maximum value. So 40, this critical number of 40, will give a maximum because the second derivative at this point is less than 0. Okay, so this is the maximum point of this downwards parabola, right? Square, we have a parabola here. And since the coefficient is negative, that is coming downwards. So 40 is the peak of this graph. Okay, but not finished just yet with part D. We want to find the quantity, which we already did here. The quantity has to be 40 bikes, but we also want to figure out what is going to be the price then per bike if 40 bikes is going to maximize our profit. So how can we figure out what the price per bike has to be if we need to produce and sell 40 bikes? By plugging 40 into our price function. Okay, so we found the quantity. So this is the quantity here. Have to figure out the price. Let me make a little line here. So now I have to figure out the price per bike. We're going to evaluate our price function at this critical number. So we're going to plug in, so again, our price function, little p of x, was 600 minus 5 times x. So now we're going to plug in 40 into our price function. So p of 40, so 600 minus 5 times 40, which gives us 200. 600 minus 200 gives us $400. So we're going to have to sell each of these 40 bikes at $400 a piece. So if we want to maximize our profit, we have to produce 40 bikes and sell these 40 bikes at $400 each. Okay. So what's going to be our maximum profit then? We found the amount of bikes we have to sell. We found the optimal quantity to sell. We found the optimal price to sell. Now to find the actual value that we're going to get, the actual maximum profit we're going to get, we have to do the following. All right, so for part, what letter am I on? E? Yeah, for part E, what is the maximum profit? Okay, well, to find our maximum profit, all we have to do is take our critical number here of our profit function, which was 40, and just like we have done before, to find our relative max or min, take that critical value and plug into the original function. Okay, so we're going to take our profit function, capital P of x, and plug in 40 into it. And so our profit function, which was, let me see here. So our profit function we call is -5 times x squared plus 400x minus 1500. So we take -5 times 40 squared plus 400 times 40 minus 1500, which is going to give us a maximum profit here of $6,500. Okay, so let's summarize what we found here then. So based on what we found from our optimal values here, the company that we have, that we're dealing with, should make 40 bikes per day and sell these bikes at a price of $400 per bike to make a maximum profit of $6,500 per day. So this company is efficient at making 40 bikes per day, and if they're able to sell all 40 bikes per day at $400 a piece, then they can make a maximum profit of $6,500 per day. Okay, so the concept's not too different from what we have done in these set of sections. To optimize means to find the critical number of that function. Okay, optimization means first derivative means critical numbers. And we'll do more examples of those in 3.4. Okay, I want to make one more note here when it comes to these business applications, because we do have another way of finding this optimal point of a profit function. All right, so again, let's talk about the relationship between revenue, cost, and profit. Nice, again, recall that the profit function, capital P of x, is defined as our revenue function. So that should be lowercase x, not big X, minus our cost function. And to maximize our profit function, to maximize P of x, like we did in that example, what we did is we found the first derivative, P prime of x, and solved for the critical numbers. Usually be just one number, but we can say critical numbers. But usually for these several problems, it will be just one critical number that we find, usually. But there can be multiple. Okay. Now, let's look at this relationship. So again, we want to find the derivative of our function to find these critical numbers in order to help us optimize it, to maximize it. Again, what is a profit function defined as? As revenue minus costs. To define the derivative of the profit function, they can also be equivalent to find the derivative of the revenue function minus the derivative of the cost function. Same thing. The derivative of the profit function is equivalent to the derivative of the revenue minus the derivative of the costs. Okay. And once we find those two derivatives, we set that difference equal to 0. So 0 is going to equal R prime minus C prime. And if we move the cost function to the other side, then notice to maximize the profit, it will be equivalent at where the first derivative of the cost function equals the first derivative of the revenue function. In other words, to maximize profit, it is equivalent to when the marginal cost equals the marginal revenue. So when the change in our cost equals the change in our revenue, that's going to maximize our profit. Because the derivative of the cost function is known as the marginal cost. The revenue is also known as the marginal revenue. Actually, I'll denote that here. All right, so when MC of X equals MR of X. The marginal cost equals the marginal revenue. That will maximize, at that point, that will maximize our profit. All right, and that will conclude here, section 3.1.